Welcome to the Lathe Soft Jaw video series, brought to you by Haas Automation. In our first video, we learned about the fundamentals of cutting lathe soft jaws when we made two different sets of OD gripping jaws. In this second video, we are once again joined by Andrew, who will now cover the important aspects of ID gripping jaws using this ring cap as an example. We also cover recutting your jaws, as well as how and when to add a taper to jaws to achieve a perfect fit. Most often, ID gripping jaws are used to hold parts, which must be completely profiled on the outside face of the part, or where the OD geometry of the part makes the surface difficult to grip. The ID bore and back face of this ring cap were completed while the workpiece was OD gripped in the first operation. And since we need to machine curved surfaces on the part's outer diameter, we need to hold it with internal gripping jaws. Andrew is considering whether to use standard soft jaws or pie jaws to ID grip this part. If he were to use regular soft jaws to hold this thin-walled part, at higher holding pressures the ring would begin to distort during clamping. Pie jaws allow this part to be clamped in a more robust and consistent manner. Pie jaws are often used to hold thin wall parts that will deform easily without full support. As shown in this graphic, gripping force is distributed much more evenly over the surface area of our pie jaws than compared to a regular soft jaw. As we covered in the previous video, we have ensured the jaws are clean before mounting, that the jaws are torqued in place, and that the chuck was lubricated at the beginning of the day using this Chuck-Ease grease. Remember, with our jaws in position for cutting, the T-nuts must be inside the chuck body. Since we'll be using these pie jaws to hold a large ID part, we can't use this style of boring ring since it will block the cutting path. Instead, Andrew will use this style of boring ring. Spinning the boring ring counterclockwise moves the three-threaded grippers outward so they can be removed. Andrew flips them around and inserts them back in the body, matching the letters on the grippers to the correct letters on the slots. The jaw grippers are now facing outward. At the chuck, Andrew places the outward-facing grippers into the screw holes in the pie jaws and clamps down. However, the jaw stroke is not at the center of travel, so the boring ring will need to be adjusted. To do this, unclamp the jaws and rotate the threaded body of the boring ring to adjust the position of the grippers. This time, with the chuck clamped, the jaws are in the middle of their stroke, right where they need to be to cut these jaws. We set the clamping pressure to 100 psi, and we'll keep the spindle speed below the recommended 900 RPM. And just as we did with OD gripping, we will need to push the jaws in the same direction that we will be ID gripping the part, this time outward against the boring ring. Take special note of how fast the spindle will be rotating during actual part machining. As speeds increase over 1000 RPM, centrifugal force acting on the jaws will begin to significantly increase gripping force as the jaws are forced outward. Chuck pressure may need to be reduced to compensate for this added force. This is another reason to consider using pie jaws. With pie jaws, the additional centrifugal jaw pressure will be spread evenly over the internal surface of the part. Regardless of what kind of ID gripping jaws you are using, jaws holding the inside diameter of the workpiece should always be cut to match the nominal workpiece diameter. With the jaws pushing outward against the boring ring at 100 psi, the master jaws at mid-stroke, and our program set to cut to the nominal part diameter, these jaws are ready to cut. As recommended in the first video, we make a narrow groove at the bottom of the jaws so that any workpiece with sharp edges will sit flush to the jaw's back face. We deburr the jaws as necessary. Now we're ready to make our part. To demonstrate how uniformly the pie jaws grip the part, Andrew mounts an indicator to check how much runout we have, with our part gripped in these jaws. At 250 psi clamp pressure, our part's total indicated runout using the pie jaws is 5/10,000ths. In contrast, with a standard set of soft jaws cut to grip this part, we see a total indicator runout of 15,000ths at 250 psi. Here is another example of a part that we want to ID grip. This pulley has sufficient wall thickness to allow us to use standard soft jaws. However, the part's inside diameter bore, which we want to grip, is so small that neither of our boring rings will fit inside of our cutting path. In this illustration, the red ring represents the cutting path needed to cut the jaws to support our pulley part. We can't mount any of our traditional boring rings in this position because we plan to cut here. One alternative is to make a custom ring to fit a groove or relief you cut into the face of the jaws. This allows for adequate clearance of the cutting path while the jaws are pushing outward against the ring, just as they will when holding the part. Although there are many factors that you should take into account when choosing regular versus pie jaws, these examples represent two possible scenarios to consider when trying to properly support your part. There are many reasons to go back and recut your soft jaws. For example, your jaws might be worn or damaged. Or maybe your parts are beginning to creep out of tolerance. Andrew plans to reuse the jaws that were originally cut to hold our bearing housing part. Since he knows that he'll be using these same jaws on this same machine with this same chuck in the future, there is no need to recut. Before disassembly, he finds a mark or feature on the master jaw and scribes a line on the soft jaws to locate them at this exact tooth position in the future. Then, as he removes each jaw, he numbers it to match the number of the corresponding master jaw on the chuck. In this way, concentricity will be maintained without cutting the jaws again. Andrew packs his jaws away and powers down the machine. As anyone who's worked in a machine shop knows, tooling sometimes has a habit of disappearing at inopportune moments. Andrew needs to run this bearing housing again, but he's found that his jaws have been used on a different machine in the shop. After finding and retrieving the jaws, he needs to recut them before he can run his parts again. Using the scribed reference marks, Andrew mounts the jaws in the exact same position as they were before. Since the idea is to machine away material to correct the jaw inaccuracies, we need to clamp OD gripping jaws to just slightly smaller than the workpiece outer diameter. Conversely, ID gripping jaws should be positioned just slightly larger than the workpiece inner diameter. We will use our part to set the initial position of the jaws as they clamp the boring ring. We want to check what diameter the jaws are actually positioned at. To do this, we program a simple move going to X0 with the tool and offset we'll be using to recut the jaws. Press hand jog, press current commands, and press page up until you reach the position page. With X-axis selected, press origin to zero out the operator position field. Now that we know where X0 is for tool 1 and offset G54, let's find the jaw face diameter. Jog to a point very close to the face of the jaws. Use a slip of paper and bring the tool to the jaw face until the paper is pinched by the insert tip. The X-axis operator field now shows us the diameter that our jaw faces are set to. In our case, we want to recut these jaws to the nominal part diameter of 3.950 inches. With our jaws checked at a clamp location of 3.935, we have set their position such that an adequate amount of material will be removed from each jaw face. We will also change our jaw cutting program to skim cut into the back face, 10 thousandths deep, to clean up this face as well as the main bore. Always skim cut the jaws for complete cleanup, but keep material removal to a minimum to get the most life out of your jaws. Now they are the correct bore size and once again concentric to the spindle. When clamping force increases, so does the deformation of the jaws. For this reason, when cutting soft jaws, it is important to try and use the same holding pressure that will be used when machining the production parts. When the pressure needed to hold the part is much higher than the pressure that was used to cut the jaws will deflect away from the part, particularly at extreme differences in clamping pressure and at very long jaw lengths. To compensate for this deflection, cutting a slight taper in the jaws may become necessary. After the taper is cut and the correct force is applied to the workpiece, the jaw faces will still be parallel to the workpiece despite jaw deflection. Let's look at some real-world scenarios. This set of short steel jaws was bored to 1 inch deep while being held at 100 psi. When we clamp this accurately machined slug at 300 psi and check for deflection, we find that we can't insert even a 1/1000th of an inch feeler gauge at the jaw tips. Next, we have these short aluminum jaws cut with a 1.5 inch deep bore, also at 100 psi. Again, we clamp the machined slug at 300 psi, and although you might think with the softer material and different clamping height we might see significant deflection, we still can't get the 1/1000th of an inch feeler gauge in between the jaw and the workpiece. To demonstrate a more extreme scenario, we move on to these tall 4-inch aluminum jaws, which were bored very deep at a clamping pressure of only 50 psi. When we clamp the demonstration workpiece at a pressure of 400 psi, jaw deflection becomes significant. Let's find out just how much taper should be added to the jaw bore. Andrew measures the space between the deflected jaw and the workpiece using the feeler gauges. He finds a 4/1000th of an inch space, so he will start by adding a 4/1000th taper to the jaws. For both outside holding and inside holding jaws, you should cut the taper to leave more material at the jaw tip than at the jaw base. Going back to his original program, Andrew changes the starting point of the cut from Z0.05 to Z0 to start right at the face of the part. He inserts U0.008 in front of the Z depth move. This will taper the face so the bore is larger diameter at the bottom than at the top. Since U0.008 is a diametrical adjustment, it will taper each wall 4/1000ths of an inch. Andrew cuts the taper in the jaws. With the taper cut and the workpiece clamped at full pressure, feeler gauges will probably not fit in the remaining space. However, there may still be a small gap. Now, Andrew uses a slow-drying bluing compound to check if he needs to make another slight taper cut. He clamps the workpiece in the jaws at full production pressure and applies a coat of the compound to the edge of the jaws where they meet the workpiece. After allowing the bluing to dry, Andrew unclamps the jaws and finds that very little of the compound has seeped in between the jaws and the workpiece, not even where the jaw tips contact the workpiece. This indicates the jaws are gripping along their entire length. Now let's look at what too much and too little taper look like using our setup. 1/1000th of an inch too much taper results in a concentration of bluing at the base of the workpiece, indicating the jaws are not contacting in this region. The inverse of this is 1/1000th of an inch too little taper, which results in good contact only at the base of the jaw, where it meets the workpiece. In either case, another pass can be made to either remove or add a slight amount of taper and thereby achieve the correct engagement. Thanks for watching this video, and stay tuned for additional episodes covering other machining fundamentals.